All right, section 3.1. Now, I hope that we'll start to think that derivatives are actually pretty cool. And actually not that bad to compute. For a while, right, up until this point, whenever we wanted to compute a derivative, f prime of x, we had to evaluate a limit of a difference quotient. The limit as h goes to 0 of f of x plus h minus f of x over h, okay? Hopefully this limit, this definition is in your head. It's going to come back on the final exam. Fortunately though, there are many shortcuts for computing derivatives. In other words, nobody really likes to take limits, and so we can, for many particular kinds of functions, we can develop shortcuts that will give us a way to compute the derivative without using the limit definition. So let's work through a bunch of these. So first, suppose f of x is equal to c, a constant. Okay? If my function is a constant, what will its derivative be? Well, its derivative will be the limit as h goes to 0 of f of x plus h minus f of x over h. But what are these function values? Right? Each of these values in the numerator is c, because the function is just always c. And so this limit is the limit as h goes to 0 of c minus c over h. C minus c, of course, is 0. And so the whole limit turns out to be 0. All right, yeah, we can keep track of these derivatives. We can say that d dx of just a constant c is equal to 0. This is kind of our first shortcut derivative formula. Another derivative that's not so hard to compute is if the function f of x is equal to x. In this case, using the limit definition, right? I use the limit definition to get the shortcuts, but once I have the shortcuts, then I'll just always do the shortcuts. So f prime of x for f of x equals x is the limit as h goes to 0 of f of x plus h minus f of x over h. Well, our particular function this time is the identity function. Whatever I plug in is what my output is. So in the first term in the numerator, when I plug in x plus h, that's also the output. So I get the limit as h goes to 0 of x plus h minus f of x, so that's minus x, all over h. What happens? The x's cancel, and then you're left with h over h. H over h, of course, is 1, and so I get the limit as h goes to 0 of 1, and I know that the limit of a constant is equal to a constant. So my answer is 1. Okay? In Leibniz notation, d dx of x is equal to 1. That's a useful formula to remember. In the last video, we found that the derivative of x squared was equal to 2x. For my next example, let's say f of x is equal to 3x squared. Sorry, no, not 3x squared. F of x is equal to x cubed. And let's find f prime of x. F prime of x is, from the definition, the limit as h goes to 0 of f of x plus h minus f of x over h. And then we plug in the values in the numerator. So that's the limit as h goes to 0 of the quantity x plus h cubed minus x cubed all over h. I need to cube out this first term here. So what will that be? That'll be, you should multiply it all out, right? X plus h times x plus h times x plus h. What you should get is x cubed plus 3x squared h plus 3x h squared plus h cubed, and then minus x cubed, all divided by h. So, now we try to simplify. Here's an x cubed minus x cubed. At this point, all of the terms in the numerator have an h in common. We've seen this many times now. So we factor that out in the numerator. What we're left with is 3x squared plus 3xh plus h squared. And in the denominator we have an h. Like we're used to, the h in the numerator and the h in the denominator cancel. And so at this point, I'm taking the limit as h goes to 0 of 3x squared plus 3xh plus h squared, and I can just plug in h equals 0. So that gives me 3x squared plus 3x times 0 plus 0 squared. The last two terms, of course, are just 0, and so my answer is 3x squared. Right, here it is again, d dx of x cubed is equal to 3x squared. If we wanted to do another one of these, right, following our kind of pattern here, right, we could show, you can try to do this on your own, you could show that d dx of x to the 4th power is equal to 4x cubed. Hopefully you're seeing the pattern, okay? Another one that you could do is d dx of x to the 5th is equal to 5x to the 4th, right? And so what we're seeing here is something called the power rule. Here's my original function, x to the 5th. To get the derivative, that 5, the original exponent, comes in front as a multiple, and then the new exponent, the exponent for the derivative, is 1 less than the original exponent. So far, all of our exponents have been positive integers. But this power rule applies no matter what the power is. It can be any real number. All right, on the handout, on your homework for today, you should have found that d dx of 1 over x is equal to minus 1 over x squared. But I can write this in a different way. d dx of 1 over x is d dx of x to the negative 1 power. Right, because I know that when I have the negative 1 power, that tells me to put the x in the denominator to the 1st power. In other words, 1 over x is really a power function, x to the minus 1. Negative 1 over x squared can also be written in a different way. That's minus 1 times x to the negative 2. Right? If I take this x squared in the denominator out of the denominator, I would have to make the exponent negative, and I could write it like this, x to the minus 2. So what I'm seeing here is that the derivative, d dx, of x to the minus 1 is minus 1 x to the minus 2, and this completely follows our pattern. Right? The negative 1, the original exponent, comes in front as a multiple, and then the new exponent, negative 2, is 1 less than the previous one, the original one, because minus 1 is equal to minus 2. Another example that I want to do is when the function f of x is equal to the square root of x. And we'll see why this is a power rule in a moment. From the definition of derivative, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Right? We're probably tired of hearing me say this by now, but it's an extremely important formula. Here's the limit as h goes to 0. For f of x plus h, I have to take x plus h, that's my input, and I plug it into the square root function. So it becomes the square root of x plus h. And then I subtract. What do I subtract? I subtract the original function f of x, which is square root of x, all over h. We've seen this form for the limit before, right? In my numerator, I have the square root, either plus or minus something. And so this is a rationalizing limit, or a multiply by the conjugate limit. So that's what we'll do. Okay, I'm just writing it over here. The limit as h goes to 0, square root of x plus h minus square root of x over h. And then I have to multiply by the conjugate of the numerator. So that's the square root of x plus h plus the square root of x, all divided by itself. Like we've seen in some examples, when you multiply by the conjugate, you have to FOIL the conjugates together. Doing that will give us what? Square root of x plus h times itself is just x plus h. My outer terms multiplied together and my inner terms multiplied together cancel. And then we have minus square root of x times plus square root of x, so that gives us a minus just x. In the denominator, I have an h times the quantity square root of x plus h plus square root of x. In the numerator, x minus x is 0, so that goes away. I'm left now with h divided by h and something else in the denominator. At this point, those h's cancel, and I'm left with a 1 in the numerator. So I'm getting the limit as h goes to 0 of 1 divided by square root of x plus h plus square root of x. And at this point, I can plug in 0 for h. That gives us 1 divided by the square root of x plus 0 plus the square root of x. And so in my denominator, I'm getting 2 square root of x. All right, that's my answer. 1 over 2 square root of x is the derivative of square root of x. And so we could write it like this. We could write d dx of square root of x as 1 over 2 square root of x. Right? I often use this formula. What I want to show us, though, is that this really is a power rule. And why is it a power rule? It's a power rule because I know that the square root function, this one right here, is also a power function. Square root of x is the same as x to the 1/2. Right, so I could write d dx of x to the 1/2 is equal, well, it has to be 1 over 2 square root of x, but then we can write that in a different way. We can write that as 1 over 2 times x to the 1/2, again, because square root of x is x to the 1/2. And then if I want, I can bring the x to the 1/2 out of the denominator by making the exponent negative. And so that would be 1 over 2 x to the minus 1/2. In other words, d dx of x to the 1/2 is 1/2 x to the minus 1/2, and that follows the power rule pattern. The 1/2 exponent comes in front as a multiple, and then the new exponent here, minus 1/2, is 1 less than the original exponent. We know that 1/2 minus 1 is minus 1/2. All right, the power rule is a very, very useful formula for us to know. I'm going to write it down just in general, and then we'll do a few more examples. Once you get the hang of the power rule, you'll probably agree that this one is very convenient and easy to apply. If n is any real number, then d dx of x raised to the nth power is equal to nx to the n minus 1. And this is our pattern, right? We bring down the old exponent, that becomes a coefficient for the derivative, and then the new exponent, n minus 1, is 1 less than the previous one, than the original one. Okay, as a quick example, if f of x is equal to x to the 21, f prime of x, the derivative is 21x to the 20. Okay, no limits required, just the power rule here. In this section, in section 3.1, they give us 3 additional rules at first, before they talk about exponential functions. We'll get to those in a second. But here are those 3 additional rules. There's something called the constant multiple rule. It says this: if I want to do the derivative of a constant times a function, right, c is a constant here, I can factor the constant out of the derivative. And so this is the same as a constant times just the derivative of the function. There's a formula for addition, and also a similar one for subtraction. Okay, so let's call this the addition formula. If I have two functions that I'm adding together, f of x plus g of x, for some reason, I might want to do the derivative of those two functions added together. And this works out very nicely. It's probably what you would expect to have. If you differentiate f plus g, that's the same as if you do the derivative of f, do the derivative of g, and then add those two derivatives together. Okay, in other words, the derivative of a sum is equal to the sum of the two separate derivatives. As you can probably guess at this point, the same idea applies for subtraction. Okay, for the subtraction rule, we can say that d dx of f of x minus g of x is equal to the difference of the two derivatives themselves. In other words, d dx of f of x minus d dx of g of x. All right, let me do one example here. Let's say that our function is f of x equals 5x to the 7 minus x squared plus 13. And then I want to try to find f prime of x. Okay, or d dx of f of x. Okay, I know that f prime of x is d dx of f of x. And so here I'm trying to do d dx of this entire function, 5x to the 7 minus x squared plus 13. Okay, how can I use my shortcuts? Well, I'm subtracting, and then I'm also adding. When I either subtract or add, I can do the derivatives separately and then combine them with the same operation. So I could write this as d dx of the first term, 5x to the 7, minus d dx of the second term, which is just x squared, and then plus d dx of the last term, which is the constant 13. Okay, this line here follows from the addition rules and the subtraction rules. How else can we simplify this? Well, in the first term, the 5 is a constant multiple. Our constant multiple rule tells us that the 5 comes outside. It can factor out of the derivative. And so this turns into 5 times d dx of x to the 7 minus d dx of x squared plus d dx of 13. If you look at this now, the derivatives that I have to compute, right, the derivative of x to the 7, the derivative of x squared, those are just both power rules, and that's a really easy rule to do. The last derivative here, the derivative of 13, is the derivative of a constant. And I know that the derivative of a constant is 0, so that one's also easy to do. Here's what we get. We get 5, and then the derivative of x to the 7 is 7x to the 6. So 5 is multiplied to 7x to the 6. And then I have a minus. The derivative of x squared from the power rule is 2x. And then I add. The derivative of a constant, 13, is 0. And so my answer here is 5 times 7, that's 35, x to the 6 minus 2x. we'll do at least one more example here in a moment. But before I do that, I want to talk about exponential functions. Remember from chapter 1 that an exponential function has the form f of x equals a to the x, where the base a is positive and not equal to 1. These are not power functions. So if I want f prime of x, right, which is what I want here, I want to try to compute this derivative, I can't do the power rule because it's not a power function, it's an exponential, okay? The number is the base instead of having the number be the exponent. So, what I can do, what I have to do at this point to compute the derivative of an exponential is I have to try to use the definition one more time. So, f prime of x will be the limit as h goes to 0 of f of x plus h minus f of x all over h. We plug in. This is the limit as h goes to 0. The first term in the numerator tells me plug x plus h into the function. So that means my exponent becomes x plus h. So that's a to the x plus h. And then I have to subtract f of x. F of x is just a to the x. And then I'm dividing by h. This limit is kind of different from limits that we've seen before. But how can I simplify this? Well, the only thing that I can really do at this point is use my laws of exponents to rewrite that first term as a product of two different exponentials. In other words, this is the limit as h goes to 0 of a to the x times a to the h minus a to the x all over h. Now, I see in my numerator that I have a to the x in common for both of those terms. So that can get factored out. So I have the limit as h goes to 0 of a to the x and then times a to the h minus 1 all over h. A to the x doesn't depend on h. In other words, it is a constant as far as h is concerned. And so it can be factored out of the limit. So what remains here? I get a to the x times the limit as h goes to 0 of a to the h minus 1 over h. This limit that I still have to compute is very similar to the limit that I started with a second ago, except what's the difference here? The difference is that x is equal to 0, right? This first term is a to the 0 plus h. And then I know if x is 0 here, that would be a to the 0, but of course a to the 0 is 1. So it does give me the second term in the numerator. So this last limit that I'm ending up with is a derivative. It's not f prime of x, it's f prime of 0. So, we can simplify further. This is a to the x, and then times f prime of 0. Okay, that's our answer at this point. All right, I'll put it up here. d dx of a to the x is equal to itself, a to the x times f prime of 0, where f prime of 0 is the derivative of f of x equals a to the x at x equals 0. This is actually very, very important because it's remarkable. The derivative of an exponential, a to the x, will exist everywhere for all x's, provided that its derivative exists at 0. Right? As long as f prime of 0 exists, then I have a formula for what the derivative of a to the x is, for any x. Another important feature of this result is that the derivative of the function a to the x is proportional, directly proportional to itself. And that's really the defining feature of an exponential, right? Exponentials grow at a rate proportional to their size. That's what this result says. And it's why exponentials are so useful in real life. It turns out, they talk about this in the book, I'll leave the reading of it to you, but I do want to write down the formula. When the base is e, which it often is, usually we use e to the x, right? That's one of our favorite exponential functions. When the base is e, we get probably the simplest derivative formula. The derivative of e to the x is equal to e to the x. Kind of boring, kind of hugely important, but hopefully easy to remember. Okay, the derivative of e to the x is just itself.